All right, let's jump right into this explainer. Today, we're taking what usually feels like a bunch of completely disconnected physics chapters, static electricity one month, circuits the next, magnets somewhere down the line, and we're going to reframe them into one grand, continuous, and honestly, awe-inspiring narrative. What if I told you it's actually all the exact same story? Today, we're diving into the physical story of charge.
So let's kick things off with a bit of a mystery. What do static cling, a humming power line, and the light from distant stars all have in common? It kind of sounds like the setup to a weird joke, right? But the answer is actually one of the most profound truths in all of physics. To really understand the light traveling from across the galaxy, we literally have to reverse engineer it all the way down to a single stationary electric charge.
To get there, we're going to follow the ultimate hero's journey of a charge. We'll track it through 4 distinct phases: static charges, moving charges, interacting fields, and finally, waves.
Now, to wrap our heads around this efficiently, we'll use a layered approach. We always want to start at the top layer with physical intuition, just asking, hey, what physically happens, before we even touch the mathematical laws or equations beneath it. From there, we move to visualization, how we picture lines and circuits, and then, finally, the real-world applications. Keeping this mental framework will make the whole progression crystal clear.
Okay, part 1. Charges at rest, the foundation of electrostatics.
Electrostatics begins with the simple existence of electric charge. You likely already know the basics here. We've got 2 flavors, positive and negative. The golden rule is that like charges repel each other, while unlike charges attract. And absolutely crucially, charge is always conserved. You can't just magic it into existence. You can only shuffle it around. This is the absolute bedrock of our whole story. Now, here's something really wild when you stop to think about it. The electrical force described by Coulomb's law perfectly parallels Newton's law of gravity. They both describe a long-range interaction where the force drops off with the square of the distance. Just like massive planets tugging on each other across the void of space, these tiny little charges are exerting pushes and pulls across distances. But how? How exactly do they reach across empty space to do that? Well, that question leads to a massive conceptual leap, because action at a distance is kind of spooky. Physicists instead defined the electric field. This means a single charge literally alters the physical space around it. It creates the surrounding physical influence. We usually visualize this with lines, pointing outward for positive, inward for negative. It's almost like a spider sitting on a web. The field is the invisible web, letting other charges know, hey, I'm over here. And those field lines, they aren't just imaginary drawings. They represent something incredibly tangible. When we look at electric potential, what we everyday folks call voltage, we see that these fields actually store energy. They point toward decreasing potential, which essentially turns our static field into a story of pent-up stored energy. And, as we know from just looking around nature, stored energy is exactly what's eventually going to force our charge to move. Which brings us to part 2, charges in motion, current electricity. When that stored potential energy is finally unleashed, the electric field acts as a driver. It forcefully pushes charges, specifically electrons, right through a conductor. On a microscopic level, they're drifting through the material. This rate of charge flow is what we call an electric current. Our protagonist isn't sitting still anymore. It is racing down the wire. And we see the real-world consequences of that motion right here. Through Ohm's law and the power equation, electrical energy is converted into actual heat and work. Voltage is the push, while resistance physically fights that motion. As the charges push through that resistance, the energy transforms into something tangible. Literally, this is the exact math that toasts your bagel in the morning and spins the motors in your fridge. But if we just stopped at toasters, we'd be missing the greatest revelation in physics. Moving to part 3, the magnetic twist, unified electromagnetism. Moving charges produce magnetic fields. This single sentence changed the world. It turns out that magnetic fields only affect moving charges, and moving charges, in turn, generate magnetic effects. This observation officially smashed electricity and magnetism together forever. They aren't 2 separate forces, they are quite literally 2 sides of the exact same coin. Mathematically, this creates a perfect parallel. Just like static charges create radiating electric fields, currents, which, remember, are just moving charges, create circulating magnetic fields around themselves. We see this through the Biot-Savart law and Ampere's law. Picture a straight copper wire with current running through it.
The magnetic field forms these invisible, continuous loops wrapping right around that wire.
But it's a two-way street, and this is where things get incredibly powerful. Enter Faraday's law of induction, which states that changing magnetic fields actually create electric fields. Think back to that physical intuition layer. Just moving a magnet near a wire physically forces the electrons inside that wire to move. This one principle, it is the absolute foundation of modern electrical generators and transformers. It's how we power human civilization.
Okay, so we've got charges making fields, fields making currents, currents making magnetism, and changing magnetism making fields again. Let's move to the climax of the story. Part 4, Let There Be Light, Self-Propagating Fields. A physicist named James Clerk Maxwell looked at Faraday's law and realized something crucial. Nature absolutely loves symmetry. If a changing magnetic field creates an electric field, Maxwell argued that a changing electric field simply must create a magnetic field too. This was his revolutionary correction. The loop was finally perfectly closed. They create each other.
The culmination of this symmetry gives us Maxwell's equations. By uniting these laws into one foundation, Maxwell mathematically proved something essentially magical. Because these two changing fields continuously create one another, they can sustain each other, endlessly leapfrogging forward through empty space. No wires required at all. Just an electric field birthing a magnetic field, which births an electric field, propagating outward forever. And the real light bulb moment, yeah, pun absolutely intended, happens when you calculate the speed of these traveling fields based on the physical constants of empty space. The result? It exactly equals the speed of light. In that moment, he proved that light is quite literally just an electromagnetic wave.
Which brings us to the ultimate conclusion, one continuous theory.
See, electromagnetism is not just a bunch of separate chapters to be memorized in isolation for a test. It's one continuous, magnificent physical story. Charge creates a field. That field drives motion. That motion causes magnetic interaction. And those interacting, changing fields lead to wave propagation. Radio waves, X-rays, the Wi-Fi you're using right now, and the visible light across the universe, they are all born from this exact same continuous chain of events.
So, I'll leave you with this. Next time you look up at the night sky and see a beam of starlight, will you recognize the journey of the single, vibrating electric charge millions of light years away that created it? I really hope this explainer has changed the way you look at the universe, and I encourage you to keep questioning the hidden, elegant connections all around us. Thanks for exploring this with me today.